In quantum mechanics, the uncertainty principle, also known as Heisenberg's uncertainty principle, is any of a variety of mathematical inequalities asserting a fundamental limit to the precision with which certain pairs of physical properties of a particle, known as complementary variables or canonically conjugate variables such as position x and momentum p, can be known. Introduced first in 1927, by the German physicist Werner Heisenberg, it states that the more precisely the position of some particle is determined, the less precisely its momentum can be known, and vice versa. The formal inequality relating the standard deviation of position sigma x and the standard deviation of momentum sigma p was derived by Earl Hess Kennard later that year and by Hermann Weyl in 1928, where h is the reduced Planck constant, h, 2 pi. Historically, the uncertainty principle has been confused with a somewhat similar effect in physics, called the observer effect, which notes that measurements of certain systems cannot be made without affecting the systems, that is, without changing something in a system. Heisenberg utilized such an observer effect at the quantum level, see below, as a physical explanation of quantum uncertainty. It has since become clearer, however, that the uncertainty principle is inherent in the properties of all wave-like systems, and that it arises in quantum mechanics simply due to the matter-wave nature of all quantum objects. Thus, the uncertainty principle actually states a fundamental property of quantum systems and is not a statement about the observational success of current technology. It must be emphasized that measurement does not mean only a process in which a physicist observer takes part, but rather any interaction between classical and quantum objects regardless of any observer. Since the uncertainty principle is such a basic result in quantum mechanics, typical experiments in quantum mechanics routinely observe aspects of it. Certain experiments, however, may deliberately test a particular form of the uncertainty principle as part of their main research program. These include, for example, tests of number-phase uncertainty relations in superconducting or quantum optics systems. Applications dependent on the uncertainty principle for their operation include extremely low noise technology such as that required in gravitational wave interferometers. Introduction. The uncertainty principle is not readily apparent on the macroscopic scales of everyday experience. So it is helpful to demonstrate how it applies to more easily understood physical situations. Two alternative frameworks for quantum physics offer different explanations for the uncertainty principle. The wave mechanics picture of the uncertainty principle is more visually intuitive, but the more abstract matrix mechanics picture formulates it in a way that generalizes more easily. Mathematically, in wave mechanics, the uncertainty relation between position and momentum arises because the expressions of the wave function in the two corresponding orthonormal bases in Hilbert space are Fourier transforms of one another, i.e., position and momentum are conjugate variables. A non-zero function and its Fourier transform cannot both be sharply localized. A similar trade-off between the variances of Fourier conjugates arises in all systems underlain by Fourier analysis. For example, in sound waves, a pure tone is a sharp spike at a single frequency, while its Fourier transform gives the shape of the sound wave in the time domain, which is a completely delocalized sine wave. In quantum mechanics, the two key points are that the position of the particle takes the form of a matter wave, and momentum is its Fourier conjugate, assured by the de Broglie relation p =, where k is the wavenumber. In matrix mechanics, the mathematical formulation of quantum mechanics, any pair of non-commuting self-adjoint operators representing observables are subject to similar uncertainty limits. An eigenstate of an observable represents the state of the wave function for a certain measurement value, the eigenvalue. For example, if a measurement of an observable A is performed, then the system is in a particular eigenstate psi of that observable. However, the particular eigenstate of the observable A need not be an eigenstate of another observable B. If so, then it does not have a unique associated measurement for it, as the system is not in an eigenstate of that observable. Wave mechanics interpretation. Ref. According to the de Broglie hypothesis, every object in the universe is a wave, i.e., a situation which gives rise to this phenomenon. The position of the particle is described by a wave function psi x t display style psi x t. The time-independent wave function of a single-moded plane wave of wave number k0 or momentum p0 is psi x e I k 0 x equals e I p 0 x. Display style psi x propto e caret ik underscore 0 x equals e caret ip underscore 0 x hbar tilde. The Born rule states that this should be interpreted as a probability density amplitude function in the sense that the probability of finding the particle between A and B is p A x B equals A B psi x 2 d x. Display style operator name p a leq x leq b equals int underscore a caret b psi x caret 2 mathrm d x tilde. In the case of the single-moded plane wave, psi x 2 display style psi x caret 2 is a uniform distribution. In other words, the particle position is extremely uncertain in the sense that it could be essentially anywhere along the wave packet. On the other hand, consider a wave function that is a sum of many waves, which we may write this as psi x n a n e I p n x. Display style psi x propto sum underscore n a underscore n e caret ip underscore n x hbar tilde, wherein represents the relative contribution of the mode Pn to the overall total. The figures to the right show how with the addition of many plane waves, the wave packet can become more localized. We may take this a step further to the continuum limit, where the wave function is an integral over all possible modes psi x equals 1 2 pi minus infinity phi p e I p x d p display style psi x equals frac 1 sqrt 2 pi hbar int underscore inft caret inft varphi p cdote caret ipx hbar dp tilde with phi p display style varphi p representing the amplitude of these modes and is called the wave function in momentum space. In mathematical terms, we say that phi p display style varphi p is the Fourier transform of psi x display style psi x, and that x and p are conjugate variables. Adding together all of these plane waves comes at a cost, namely the momentum has become less precise, having become a mixture of waves of many different momenta. One way to quantify the precision of the position and momentum is the standard deviation sigma. Since psi x 2 display style psi x caret 2 is a probability density function for position, we calculate its standard deviation. The precision of the position is improved, i.e. reduced sigma x, by using many plane waves, thereby weakening the precision of the momentum, i.e. increased sigma p. Another way of stating this is that sigma x and sigma p have an inverse relationship or are at least bounded from below. This is the uncertainty principle, the exact limit of which is the Canard bound. Click the Show button below to see a semi-formal derivation of the Canard inequality using wave mechanics. Matrix mechanics interpretation. Ref. In matrix mechanics, observables such as position and momentum are represented by self-adjoint operators. When considering pairs of observables, an important quantity is the commutator. For a pair of operators A and B, one defines their commutator as A caret B caret equals A caret B caret minus B caret A caret display style hat A hat B equals hat A hat B hat B hat A. In the case of position and momentum, the commutator is the canonical commutation relation x caret p caret equals I. Display style hat x hat p equals I hbar. The physical meaning of the non-commutativity can be understood by considering the effect of the commutator on position and momentum eigenstates. Let psi display style psi wrangle be a right eigenstate of position with a constant eigenvalue x0. By definition, this means that x caret psi equals x 0 psi display style hat x psi wrangle equals x underscore 0 psi wrangle. Applying the commutator to psi display style psi wrangle yields x caret p caret psi equals x caret p caret minus p caret x caret psi equals x caret minus x 0 I caret p caret psi equals I psi display style hat x hat p psi wrangle equals hat x hat p hat x psi wrangle equals hat x x underscore 0 hat I hat p psi wrangle equals I hbar psi wrangle, where I is the identity operator. Suppose, for the sake of proof by contradiction, that psi display style psi wrangle is also a right eigenstate of momentum, with constant eigenvalue p0. If this were true, then one could write x caret minus x 0 I caret p caret psi equals x caret minus x 0 I caret p 0 psi equals x 0 I caret minus x 0 I caret p 0 psi equals 0. Display style hat x x underscore 0 hat I hat p psi wrangle equals hat x x underscore 0 hat I p underscore 0 psi wrangle equals x underscore 0 hat I x underscore 0 hat I p underscore 0 psi wrangle equals 0. On the other hand, the above canonical commutation relation requires that x caret p caret psi equals I psi does not equal 0. Display style hat x hat p psi wrangle equals I hbar psi wrangle neq 0. This implies that no quantum state can simultaneously be both a position and a momentum eigenstate. When a state is measured, it is projected onto an eigenstate in the basis of the relevant observable. For example, if a particle's position is measured, then the state amounts to a position eigenstate. This means that the state is not a momentum eigenstate, however, but rather it can be represented as a sum of multiple momentum basis eigenstates. In other words, the momentum must be less precise. This precision may be quantified by the standard deviations sigma x equals x caret 2 minus x caret 2. Display style sigma underscore x equals sqrt Langle hat x caret 2 Langle hat x Rangle caret 2 sigma p equals p caret 2 minus p caret 2. Display style sigma underscore p equals sqrt Langle hat p caret 2 Rangle hat p Rangle caret 2. As in the wave mechanics interpretation above, one sees a trade-off between the respective precisions of the two, quantified by the uncertainty principle. Robertson–Schrödinger uncertainty relations. The most common general form of the uncertainty principle is the Robertson uncertainty relation, for an arbitrary Hermitian operator O caret #mathcall O. We can associate a standard deviation sigma O equals O caret 2 minus O caret 2. Display style sigma underscore math call O equals sqrt Langle hat math call O caret 2 Rangle hat math call O Rangle caret 2, where the brackets O display style Langle math call O Rangle indicate an expectation value. For a pair of operators A caret display style hat A and B caret display style hat B, we may define their commutator as A caret B caret equals A caret B caret minus B caret A caret. Display style hat A hat B equals hat A hat B hat B hat A. In this notation, the Robertson uncertainty relation is given by sigma A sigma B 1 2 I A caret B caret equals 1 2 A caret B caret Display style sigma underscore b geq left frac 1 2 I langle hat b wrangle right equals frac 1 2 left langle hat b wrangle right. The Robertson uncertainty relation immediately follows from a slightly stronger inequality, the Schrödinger uncertainty relation, where we have introduced the anti-commutator a caret b caret equals a caret b caret plus b caret a caret. Display style hat b equals hat a hat b plus hat b hat a. Topic Examples. Since the Robertson and Schrödinger relations are for general operators, the relations can be applied to any two observables to obtain specific uncertainty relations. A few of the most common relations found in the literature are given below. For position and linear momentum, the canonical commutation relation x caret p caret equals I. Display style hat x hat p equals I hbar implies the canard inequality from above. Sigma x sigma p 2. Display style sigma underscore x sigma underscore p geq frac hbar 2 for two orthogonal components of the total angular momentum operator of an object. Sigma j I sigma j 2 j k. Display style sigma underscore j underscore I sigma underscore j underscore j geq frac hbar 2 big langle j underscore k wrangle big, where I, j, k are distinct, and g denotes angular momentum along the xi axis. This relation implies that unless all three components vanish together, only a single component of a system's angular momentum can be defined with arbitrary precision, normally the component parallel to an external magnetic or electric field. Moreover, for j x j y equals I epsilon x y z j z. Display style j underscore x j underscore y equals I hbar var epsilon underscore x y z j underscore z. A choice a caret equals j x. Display style hat a equals j underscore x b caret equals j y. Display style hat b equals j underscore y. In angular momentum multiplets, psi equals J m bounds the Casimir invariant angular momentum squared J x 2 plus J y 2 plus J z 2 display style Langle J underscore x caret 2 plus J underscore y caret 2 plus J underscore z caret 2 wrangle from below, and thus yields useful constraints such as J plus 1 m plus 1 and hence Jm among others. In non-relativistic mechanics, time is privileged as an independent variable. Nevertheless, in 1945, L. I. Mandelstam and I. E. Tam derived a non-relativistic time-energy uncertainty relation, as follows. For a quantum system in a non-stationary state psi and an observable B represented by a self-adjoint operator B caret display style hat B. The following formula holds: sigma E sigma B D B caret D T 2 display style sigma underscore E frac sigma underscore B left frac mathrm D Langle hat B wrangle mathrm D T right geq frac hbar 2 where sigma E is the standard deviation of the energy operator Hamiltonian in the state psi, sigma B stands for the standard deviation of B. Although the second factor in the left-hand side has dimension of time, it is different from the time parameter that enters the Schrödinger equation. It is a lifetime of the state psi with respect to the observable B. In other words, this is the time interval delta t after which the expectation value B caret display style Langle hat B wrangle changes appreciably. An informal, heuristic meaning of the principle is the following: a state that only exists for a short time cannot have a definite energy. To have a definite energy, the frequency of the state must be defined accurately, and this requires the state to hang around for many cycles, the reciprocal of the required accuracy. For example, in spectroscopy, excited states have a finite lifetime. By the time-energy uncertainty principle, they do not have a definite energy, and, each time they decay, the energy they release is slightly different. The average energy of the outgoing photon has a peak at the theoretical energy of the state, but the distribution has a finite width called the natural linewidth. Fast decaying states have a broad linewidth, while slow decaying states have a narrow linewidth. The same linewidth effect also makes it difficult to specify the rest mass of unstable, fast decaying particles in particle physics. The faster the particle decays, the shorter its lifetime, the less certain is its mass, the larger the particle's width, for the number of electrons in a superconductor and the phase of its Ginzburg-Landau order parameter delta n delta phi 1. Display style delta n delta var phi geq1. Topic: a counterexample. Suppose we consider a quantum particle on a ring, where the wave function depends on an angular variable theta theta, which we may take to lie in the interval 0 2 pi 0 2 pi. Define position and momentum operators a caret hat a and b caret hat b by a caret psi theta equals theta psi theta theta element of 0 2 pi display style hat a psi theta equals theta psi theta quad theta in 0 2 pi and b caret psi equals minus I d psi d theta display style hat b psi equals I hbar frac d psi d theta, where we impose periodic boundary conditions on b caret display style hat b. Note that the definition of a caret display style hat a depends on our choice to have theta display style theta range from 0 to 2 pi display style 2 pi. These operators satisfy the usual commutation relations for position and momentum operators. A caret b caret equals I display style hat a hat b equals I hbar. Now let psi display style psi be any of the eigenstates of b caret display style hat b, which are given by psi theta equals e 2 pi I n theta display style psi theta equals e caret 2 pi in theta. Note that these states are normalizable, unlike the eigenstates of the momentum operator on the line. Note also that the operator a caret display style hat a is bounded, since theta display style theta ranges over a bounded interval. Thus, in the state psi display style psi, the uncertainty of b display style b is 0 and the uncertainty of a display style a is finite, so that sigma a sigma b equals 0. Display style sigma underscore a sigma underscore b equals 0. Although this result appears to violate the Robertson uncertainty principle, the paradox is resolved when we note that psi display style psi is not in the domain of the operator b caret a caret display style hat b hat a, since multiplication by theta display style theta disrupts the periodic boundary conditions imposed on b caret display style hat b. Thus, the derivation of the Robertson relation, which requires a caret b caret psi display style hat a hat b psi and b caret a caret psi display style hat b hat a psi to be defined does not apply. These also furnish an example of operators satisfying the canonical commutation relations but not the Weyl relations. For the usual position and momentum operators x caret display style hat x and p caret display style hat p on the real line, no such counterexamples can occur. As long as sigma x display style sigma underscore x and sigma p display style sigma underscore p are defined in the state psi display style psi. The Heisenberg uncertainty principle holds even if psi display style psi fails to be in the domain of x caret p caret display style hat x hat p or of p caret x caret display style hat p hat x. Topic examples. Refs. Topic quantum harmonic oscillator stationary states. Consider a one-dimensional quantum harmonic oscillator QHO. It is possible to express the position and momentum operators in terms of the creation and annihilation operators x caret equals 2 m omega a plus a display style hat x equals sqrt frac hbar 2 meters omega a plus a caret dagger p caret equals I m omega 2 a minus a display style hat p equals I sqrt frac m omega hbar 2 a caret dagger a. Using the standard rules for creation and annihilation operators on the eigenstates of the QHO, a n equals n plus 1 n plus 1 display style a caret dagger n rangle equals sqrt n plus 1 n plus 1 rangle a n equals n n minus 1 display style a n rangle equals sqrt n n1 rangle. The variances may be computed directly. Sigma x 2 equals m omega n plus 1 2 display style sigma underscore x caret 2 equals frac hbar m omega left n plus frac 1 2 right. Sigma p 2 equals m omega n plus 1 2 display style sigma underscore p caret 2 equals hbar m omega left n plus frac 1 2 right. The product of these standard deviations is then sigma x sigma p equals n plus 1 2 2 display style sigma underscore x sigma underscore p equals hbar left n plus frac 1 2 right geq frac hbar 2 tilde. In particular, the above canard bound is saturated for the ground state n equals 0, for which the probability density is just the normal distribution. Quantum harmonic oscillator with Gaussian initial condition. In a quantum harmonic oscillator of characteristic angular frequency omega, place a state that is offset from the bottom of the potential by some displacement x0 as psi x equals m omega pi 1 4 exp minus m omega x minus x 0 2 2 display style psi x equals left frac m omega pi hbar right caret 1/4 exp left frac m omega x underscore 0 caret 2 2 hbar right, where omega describes the width of the initial state but need not be the same as omega. Through integration over the propagator, we can solve for the full time-dependent solution. After many cancellations, the probability densities reduce to psi x t 2 n x 0 cos omega t 2 m omega cos 2 omega t plus omega 2 omega 2 sin 2 omega t. Display style psi x t caret 2 sim math call n left x underscore 0 cos omega t frac hbar 2 meters omega left cos caret 2 omega t plus frac omega caret 2 omega caret 2 sin caret 2 omega t right phi p t 2 n minus m x 0 omega sin omega t m omega 2 cos 2 omega t plus omega 2 omega 2 sin 2 omega t. Display style phi p t caret 2 sim math call n left mx underscore 0 omega sin omega t frac hbarm omega 2 left cos caret 2 omega t plus frac omega caret 2 omega caret 2 sin caret 2 omega t right. Where we have used the notation n mu sigma 2 display style math call n mu sigma caret 2 to denote a normal distribution of mean mu and variance sigma 2. Copying the variances above and applying trigonometric identities, we can write the product of the standard deviations as sigma x sigma p equals 2 cos 2 omega t plus omega 2 omega 2 sin 2 omega t cos 2 omega t plus omega 2 omega 2 sin 2 omega t equals 4 3 plus 1 2 omega 2 omega 2 plus omega 2 ohms 2 minus 1 2 omega 2 plus omega 2 ohms 2 minus 1 cos 4 omega t display style begin aligned sigma underscore x sigma underscore p and equals frac hbar 2 sqrt left cos caret 2 omega t plus frac omega caret 2 omega caret 2 sin caret 2 omega t rig t left cos caret 2 omega t plus frac omega caret 2 omega caret 2 sin caret 2 omega t right and equals frac hbar 4 sqrt 3 plus frac 1 2 left frac omega caret 2 omega caret 2 plus frac omega caret 2 omega caret 2 right left frac 1 2 left frac omega caret 2 omega caret 2 plus frac omega caret 2 omega caret 2 right minus 1 right cos 4 omega t end aligned from the relations omega 2 plus omega 2 ohms 2 2 cos 4 omega t 1 display style frac omega caret 2 omega caret 2 plus frac omega caret 2 omega caret 2 geq 2 quad cos 4 omega t leq 1 we can conclude the following: the right-most equality holds only when omega equals omega sigma x sigma p 4 3 plus 1 2 omega 2 omega 2 plus omega 2 omega 2 minus 1 2 omega 2 omega 2 plus omega 2 omega 2 minus 1 equals 2. Display style sigma underscore x sigma underscore p geq frac hbar 4 sqrt 3 plus frac 1 2 left frac omega caret 2 omega caret 2 plus frac omega caret 2 omega caret 2 right left frac 1 2 left frac omega caret 2 omega caret 2 plus frac omega caret 2 omega caret 2 right minus 1 right equals frac hbar 2. Topic: Coherent states. A coherent state is a right eigenstate of the annihilation operator a caret alpha equals alpha alpha. Display style hat a alpha rangle equals alpha alpha rangle, which may be represented in terms of Fock states as alpha equals E minus alpha 2 n equals 0 infinity alpha n n n display style alpha rangle equals e caret alpha caret 2 over 2 sum underscore n equals 0 caret inft alpha caret n over sqrt n n rangle. In the picture where the coherent state is a massive particle in a QHO. The position and momentum operators may be expressed in terms of the annihilation operators in the same formulas above and used to calculate the variances sigma x 2 equals 2 m omega. Display style sigma underscore x caret 2 equals frac hbar 2 meters omega sigma p 2 equals m omega 2. Display style sigma underscore p caret 2 equals frac hbarm omega 2. Therefore, every coherent state saturates the canard bound sigma x sigma p equals 2 m omega m omega 2 equals 2. Display style sigma underscore x sigma underscore p equals sqrt frac hbar 2 meters omega sqrt frac hbarm omega 2 equals frac hbar 2, with position and momentum each contributing an amount 2. Display style sqrt hbar 2 in a balanced way. Moreover, every squeezed coherent state also saturates the canard bound, although the individual contributions of position and momentum need not be balanced in general. Topic: Particle in a box. Consider a particle in a one-dimensional box of length L. Display style L. The eigenfunctions in position and momentum space are psi n x t equals a sin k n x e minus I omega n t 0 x L 0. Otherwise, display style psi underscore n x t equals begin cases a sin k underscore n x mathrm e caret mathrm I omega underscore n t and 0 and phi n p t equals pi ln 1 minus 1 n e minus I k L E minus I omega n T pi 2 n 2 minus k 2 L 2. display style varphi underscore n p t equals sqrt frac pi l hbar frac n left 1 minus 1 caret n e caret I k l right e caret I omega underscore n t pi caret 2 n caret 2 k caret 2 l caret 2, where omega n equals pi 2 n 2 8 l 2 m. Display style omega underscore n equals frac pi caret 2 hbarn caret 2 8 l caret 2 m, and we have used the de Broglie relation p equals k. Display style p equals hbark. The variances of x display style x and p display style p can be calculated explicitly. Sigma x 2 equals l 2 12 1 minus 6 n 2 pi 2. Display style sigma underscore x caret 2 equals frac l caret 2 12 left 1 frac 6 n caret 2 pi caret 2 right. Sigma p 2 equals n pi l 2. Display style sigma underscore p caret 2 equals left frac hbarn pi l right caret 2. The product of the standard deviations is therefore sigma x sigma p equals 2 n 2 pi 2 3 minus 2. Display style sigma underscore x sigma underscore p equals frac hbar 2 sqrt frac n caret 2 pi caret 2 3 minus 2 for all n equals 1 2 3. Display style n equals 1 2 3 l dots. The quantity n 2 pi 2 3 minus 2. Display style sqrt frac n caret 2 pi caret 2 3 minus 2 is greater than 1, so the uncertainty principle is never violated. For numerical concreteness, the smallest value occurs when n equals 1. Display style n equals 1, in which case sigma x sigma p equals 2 pi 2 3 minus 2 approximately equals 0.568 greater than 2. Display style sigma underscore x sigma underscore p equals frac hbar 2 sqrt frac pi caret 2 3 minus 2 approximately 0.568 hbar greater than frac hbar 2. Constant momentum. Assume a particle initially has a momentum space wave function described by a normal distribution around some constant momentum p0 according to phi p equals x 0 pi 1 2 exp minus x 0 2 p minus p 0 2 2 2. Display style var p equals left frac x underscore 0 hbar sqrt pi right caret 1/2 c dot exp left frac x underscore 0 caret 2 pp underscore 0 caret 2 2 hbar caret 2 right, where we have introduced a reference scale x 0 equals m omega 0. Display style x underscore 0 equals sqrt hbar per meter omega underscore 0, with omega 0 greater than 0. Display style omega underscore 0 greater than 0, describing the width of the distribution minus cf. Nondimensionalization. If the state is allowed to evolve in free space, then the time-dependent momentum and position space wave functions are phi p t equals x 0 pi 1 2 exp minus x 0 2 p minus p 0 2 2 2 minus I p 2 t 2 m. Display style phi p t equals left frac x underscore 0 hbar sqrt pi right caret 1/2 c dot exp left frac x underscore 0 caret 2 pp underscore 0 caret 2 2 hbar caret 2 frac ip caret 2 t 2 meters hbar right psi x t equals 1 x 0 pi 1 2 e minus x 0 2 p 0 2 2 2 1 plus I omega 0 t exp minus x minus I x 0 2 p 0 2 2 x 0 2 1 plus I omega 0 t display style psi x t equals left frac 1 x underscore 0 sqrt pi right caret 1/2 c dot frac e caret x underscore 0 caret 2 p underscore 0 caret 2 2 hbar caret 2 sqrt 1 plus I omega underscore 0 t c dot exp left frac xx underscore 0 caret 2 p underscore 0 hbar caret 2 2 x underscore 0 caret 2 1 plus I omega underscore 0 t right. Since p t equals p 0 display style Langle p t rangle equals p underscore 0 and sigma p t equals x 0 2 display style sigma underscore p t equals hbar x underscore 0 sqrt 2. This can be interpreted as a particle moving along with constant momentum at arbitrarily high precision. On the other hand, the standard deviation of the position is sigma x equals x 0 2 1 plus omega 0 2 t 2 display style sigma underscore x equals frac x underscore 0 sqrt 2 sqrt 1 plus omega underscore 0 caret 2 t caret 2 such that the uncertainty product can only increase with time as sigma x t sigma p t equals 2 1 plus omega 0 2 t 2 display style sigma underscore x t sigma underscore p t equals frac hbar 2 sqrt 1 plus omega underscore 0 caret 2 t caret 2. Topic: Additional uncertainty relations. Topic: Mixed states. The Robertson–Schrödinger uncertainty relation may be generalized in a straightforward way to describe mixed states. Sigma a 2 sigma b 2 1 2 tr rho a b minus tr rho a tr rho b 2 plus 1 2 I tr rho a b 2. Display style sigma underscore a caret 2 sigma underscore b caret 2 geq left frac 1 2 operatorname tr rho a b operatorname tr rho a operatorname tr rho b right caret 2 plus left frac 1 2 I operatorname tr rho a b right caret 2. Topic: The Maccone-Pati uncertainty relations. The Robertson–Schrödinger uncertainty relation can be trivial if the state of the system is chosen to be eigenstate of one of the observable. The stronger uncertainty relations proved by Maccone and Pati give non-trivial bounds on the sum of the variances for two incompatible observables. For two non-commuting observables a _a and b _b. The first stronger uncertainty relation is given by sigma a 2 plus sigma b 2 plus or minus I psi a b psi plus psi a plus or minus I b psi 2. Display style sigma underscore a caret 2 plus sigma underscore b caret 2 geq pmi Langle psi mid a b psi wrangle plus mid Langle psi mid a pm ib mid bar psi wrangle caret 2, where sigma a 2 equals psi a 2 psi minus psi a psi 2. Display style E sigma underscore a caret 2 equals Langle psi a caret 2 psi wrangle Langle psi mid a mid psi wrangle caret 2 sigma b 2 equals psi b 2 psi minus psi b psi 2. Display style sigma underscore b caret 2 equals Langle psi b caret 2 psi wrangle Langle psi mid b mid psi wrangle caret 2 psi display style bar psi wrangle is a normalized vector that is orthogonal to the state of the system psi display style psi wrangle, and one should choose the sign of plus or minus I psi a b psi display style PMI Langle psi mid a b mid psi wrangle to make this real quantity a positive number. The second stronger uncertainty relation is given by sigma a 2 plus sigma b 2 1 2 psi a plus b a plus b psi 2 display style sigma underscore a caret 2 plus sigma underscore b caret 2 geq frac 1 2 Langle bar psi underscore a plus b mid psi wrangle caret 2 where psi a plus b display style bar psi underscore a plus b wrangle is a state orthogonal to psi display style psi wrangle. The form of psi a plus b display style bar psi underscore a plus b wrangle implies that the right-hand side of the new uncertainty relation is non-zero unless psi display style psi wrangle is an eigenstate of a plus b display style a plus b. One may note that psi display style psi wrangle can be an eigenstate of a plus b display style a plus b without being an eigenstate of either a display style a or b display style b. However, when psi display style psi wrangle is an eigenstate of one of the two observables, the Heisenberg-Schrödinger uncertainty relation becomes trivial. But the lower bound in the new relation is non-zero unless psi display style psi wrangle is an eigenstate of both. Topic: Phase space. In the phase space formulation of quantum mechanics, the Robertson–Schrödinger relation follows from a positivity condition on a real star square function. Given a Wigner function W x p display style W x p with star product and a function f, the following is generally true: f equals f W x p d x d p 0. Display style Langle f caret asterisk star f rangle equals int f caret asterisk star f w x p dx dp geq 0. Choosing f equals a plus b x plus c p display style f equals a plus bx plus cp, we arrive at f equals a b c 1 x p x x x x p ppxpp a b c 0. Display style Langle f caret asterisk star f rangle equals begin b matrix a caret asterisk and b caret asterisk and c caret asterisk end b matrix begin b matrix 1 and Langle x wrangle and Langle p wrangle Langle x wrangle and Langle x star x wrangle and Langle x star p wrangle Langle p wrangle and Langle p star x wrangle and Langle p star p wrangle end b matrix begin b matrix a b c end b matrix geq 0. Since this positivity condition is true for all a, b, and c, it follows that all the eigenvalues of the matrix are positive. The positive eigenvalues then imply a corresponding positivity condition on the determinant det 1 x p x x x x p p p x p p equals det 1 x p x x 2 x p plus I2pxp minus I2p2 0. Display style det begin b matrix 1 and Langle x wrangle and Langle p wrangle Langle x wrangle and Langle x star x wrangle and Langle x star p wrangle Langle p wrangle and Langle p star x wrangle and Langle p star p wrangle end b matrix equals det begin b matrix 1 and Langle x wrangle and Langle p wrangle Langle x wrangle and Langle x caret 2 wrangle and left Langle xp plus frac I hbar 2 right wrangle Langle p wrangle and left Langle xp frac I hbar 2 right wrangle and Langle p caret 2 wrangle end b matrix geq 0, or explicitly, after algebraic manipulation, sigma x2 sigma p2 equals x2 minus x2 p2 minus p2 x p minus x p 2 plus 2 4 Display style sigma underscore x caret 2 sigma underscore p caret 2 equals left Langle x caret 2 wrangle x wrangle caret 2 right left Langle p caret 2 wrangle p wrangle caret 2 right geq left Langle xp wrangle x wrangle p wrangle right caret 2 plus frac hbar caret 2 4 tilde. Topic: Systematic and statistical errors. The inequalities above focus on the statistical imprecision of observables as quantified by the standard deviation sigma. Display style sigma. Heisenberg's original version, however, was dealing with the systematic error, a disturbance of the quantum system produced by the measuring apparatus, i.e., an observer effect. If we let epsilon a display style var epsilon underscore a represent the error, i.e., inaccuracy of a measurement of an observable A and eta b display style eta underscore b. The disturbance produced on a subsequent measurement of the conjugate variable b by the former measurement of A, then the inequality proposed by Ozawa, encompassing both systematic and statistical errors, holds. Heisenberg's uncertainty principle, as originally described in the 1927 formulation, mentions only the first term of Ozawa inequality, regarding the systematic error. Using the notation above to describe the error-disturbance effect of sequential measurements first A, then B, it could be written as the formal derivation of the Heisenberg relation is possible but far from intuitive. It was not proposed by Heisenberg, but formulated in a mathematically consistent way only in recent years. Also, it must be stressed that the Heisenberg formulation is not taking into account the intrinsic statistical errors sigma a display style sigma underscore a and sigma b display style sigma underscore b. There is increasing experimental evidence that the total quantum uncertainty cannot be described by the Heisenberg term alone, but requires the presence of all the three terms of the Ozawa inequality. Using the same formalism, it is also possible to introduce the other kind of physical situation, often confused with the previous one, namely the case of simultaneous measurements A and B at the same time. The two simultaneous measurements on A and B are necessarily unsharp or weak. It is also possible to derive an uncertainty relation that, as the Ozawa's one, combines both the statistical and systematic error components, but keeps a form very close to the Heisenberg original inequality. By adding Robertson and Ozawa relations we obtain epsilon a eta b plus epsilon a sigma b plus sigma a eta b plus sigma a sigma b a caret b caret display style var epsilon underscore a eta underscore b plus var epsilon underscore a sigma underscore b plus sigma underscore a eta underscore b plus sigma underscore a sigma underscore b geq left langle hat a hat b wrangle right. The four terms can be written as epsilon a plus sigma a eta b plus sigma b a caret b caret. Display style var epsilon underscore a plus sigma underscore a eta underscore b plus sigma underscore b geq left langle hat a hat b wrangle right. Defining epsilon a epsilon a plus sigma a display style bar var epsilon underscore a equiv var epsilon underscore a plus sigma underscore a as the inaccuracy in the measured values of the variable a and eta b eta b plus sigma b display style bar eta underscore b equiv eta underscore b plus sigma underscore b as the resulting fluctuation in the conjugate variable b. Fujikawa established an uncertainty relation similar to the Heisenberg original one, but valid both for systematic and statistical errors. Quantum entropic uncertainty principle. For many distributions, the standard deviation is not a particularly natural way of quantifying the structure. For example, uncertainty relations in which one of the observables is an angle has little physical meaning for fluctuations larger than one period. Other examples include highly bimodal distributions, or unimodal distributions with divergent variance. A solution that overcomes these issues is an uncertainty based on entropic uncertainty instead of the product of variances. While formulating the many worlds interpretation of quantum mechanics in 1957, Hugh Everett III conjectured a stronger extension of the uncertainty principle based on entropic certainty. This conjecture, also studied by Hirschman and proven in 1975 by Beckner and by Iwo Bialicki Barula and Jerzy Michalski, is that, for two normalized, dimensionless Fourier transform pairs f a and g b, where f a equals minus infinity g b e 2 pi I a b d b display style f a equals int underscore inft caret inft g b e caret 2 pi I a b d b and g b equals minus infinity f a e minus 2 pi I A B D A display style G B equals int underscore inft caret inft F A E caret minus 2 pi I A B da. The Shannon information entropies H A equals minus infinity F A log F A D A display style H underscore a equals int underscore inft caret inft F A log F A da and H B equals minus infinity G B log G B D B display style H underscore B equals int underscore inft caret inft G B log G B D B are subject to the following constraint, where the logarithms may be in any base. The probability distribution functions associated with the position wave function psi x and the momentum wave function phi x have dimensions of inverse length and momentum respectively, but the entropies may be rendered dimensionless by h x equals minus psi x 2 lane x 0 psi x 2 d x equals minus lane x 0 psi x 2 display style H underscore x equals int psi x caret 2 lane x underscore 0 psi x caret 2 dx equals left langle lane x underscore 0 mid psi x caret 2 right wrangle H P equals minus phi P 2 lane P 0 phi P 2 D P equals minus lane P 0 phi P 2 display style H underscore P equals int var phi P caret 2 lane P underscore 0 var phi P caret 2 dP equals left langle lane P underscore 0 left var phi P right caret 2 right wrangle, where x0 and p0 are some arbitrarily chosen length and momentum respectively, which render the arguments of the logarithms dimensionless. Note that the entropies will be functions of these chosen parameters. Due to the Fourier transform relation between the position wave function psi x and the momentum wave function phi p, the above constraint can be written for the corresponding entropies as where h is Planck's constant. Depending on one's choice of the x0 p0 product, the expression may be written in many ways. If x0 p0 is chosen to be h, then h x plus h p log e 2 display style h underscore x plus h underscore p geq log left frac e 2 right. If instead x0 p0 is chosen to be h, then h x plus h p log e pi display style h underscore x plus h underscore p geq log e pi. If x0 and p0 are chosen to be unity in whatever system of units are being used, then h x plus h p log e h 2 display style h underscore x plus h underscore p geq log left frac e h 2 right, where h is interpreted as a dimensionless number equal to the value of Planck's constant in the chosen system of units. The quantum entropic uncertainty principle is more restrictive than the Heisenberg uncertainty principle. From the inverse logarithmic Sobolev inequalities, h x 1 2 log 2 e pi sigma x 2 x 0 2 display style h underscore x leq frac 1 2 log 2 e pi sigma underscore x caret 2 x underscore 0 caret 2 tilde h p 1 2 log 2 e pi sigma p 2 p 0 2 display style h underscore p leq frac 1 2 log 2 e pi sigma underscore p caret 2 p underscore 0 caret 2 tilde. Equivalently, from the fact that normal distributions maximize the entropy of all such with a given variance, it readily follows that this entropic uncertainty principle is stronger than the one based on standard deviations, because sigma x sigma p 2 exp h x plus h p minus log e h 2 x 0 p 0 2 Display style sigma underscore x sigma underscore p geq frac hbar 2 exp left h underscore x plus h underscore p log left frac e h 2 x underscore 0 p underscore 0 right geq frac hbar 2 tilde. In other words, the Heisenberg uncertainty principle is a consequence of the quantum entropic uncertainty principle, but not vice versa. A few remarks on these inequalities. First, the choice of base E is a matter of popular convention in physics. The logarithm can alternatively be in any base, provided that it be consistent on both sides of the inequality. Second, recall the Shannon entropy has been used, not the quantum von Neumann entropy. Finally, the normal distribution saturates the inequality, and it is the only distribution with this property, because it is the maximum entropy probability distribution among those with fixed variance cf. Here for proof. A measurement apparatus will have a finite resolution set by the discretization of its possible outputs into bins, with the probability of lying within one of the bins given by the Born rule. We will consider the most common experimental situation, in which the bins are of uniform size. Let delta x be a measure of the spatial resolution. We take the zeroth bin to be centered near the origin, with possibly some small constant offset c. The probability of lying within the jth interval of width delta x is p x j equals j minus 1 2 delta x minus c j plus 1 2 delta x minus c psi x 2 d x. Display style operator name p x underscore j equals int underscore j minus 1/2 delta x c caret j plus 1/2 delta x c psi x caret 2 dx. To account for this discretization, we can define the Shannon entropy of the wave function for a given measurement apparatus as h x equals minus j equals minus infinity p x j lane p x j. Display style h underscore x equals sum underscore j equals inft caret inft operator name p x underscore j lane operator name p x underscore j. Under the above definition, the entropic uncertainty relation is h x plus h p greater than lane east 2 minus lane delta x delta p h display style h underscore x plus h underscore p greater than lane left frac east 2 right lane left frac delta x delta p h right. Here we note that delta x delta p h is a typical infinitesimal phase space volume used in the calculation of a partition function. The inequality is also strict and not saturated. Efforts to improve this bound are an active area of research. Harmonic analysis. In the context of harmonic analysis, a branch of mathematics, the uncertainty principle implies that one cannot at the same time localize the value of a function and its Fourier transform. To wit, the following inequality holds: minus infinity x 2 f x 2 d x minus infinity she 2 f caret she 2 d she f 2 4 16 pi 2 display style left int underscore inft caret inft x caret 2 f x caret 2 dx right left int underscore inft caret inft she caret 2 hat f she caret 2 d she right geq frac f underscore 2 caret 4 16 pi caret 2. Further mathematical uncertainty inequalities, including the above entropic uncertainty, hold between a function f and its Fourier transform h x plus h she log e 2 display style h underscore x plus h underscore she geq log e 2. Topic: Signal processing. In the context of signal processing, and in particular time-frequency analysis, uncertainty principles are referred to as the Gabor limit, after Dennis Gabor, or sometimes the Heisenberg-Gabor limit. The basic result, which follows from Benedicks' theorem below, is that a function cannot be both time-limited and band-limited. A function and its Fourier transform cannot both have bounded domain. See band-limited versus time-limited. Thus, sigma t sigma f 1 4 pi approximately equals 0.08 cycles. Display style sigma underscore t cdot sigma underscore f geq frac 1 4 pi approximately 0.08 text cycles, where sigma t display style sigma underscore t and sigma f display style sigma underscore f are the standard deviations of the time and frequency estimates respectively. Stated alternatively, one cannot simultaneously sharply localize a signal function f in both the time domain and frequency domain, its Fourier transform. When applied to filters, the result implies that one cannot achieve high temporal resolution and frequency resolution at the same time. A concrete example are the resolution issues of the short-time Fourier transform. If one uses a wide window, one achieves good frequency resolution at the cost of temporal resolution, while a narrow window has the opposite trade-off. Alternate theorems give more precise quantitative results, and, in time-frequency analysis, rather than interpreting the one-dimensional time and frequency domains separately, one instead interprets the limit as a lower limit on the support of a function in the two-dimensional time-frequency plane. In practice, the Gabor limit limits the simultaneous time-frequency resolution one can achieve without interference. It is possible to achieve higher resolution, but at the cost of different components of the signal interfering with each other. Topic: DFT-Uncertainty principle. There is an uncertainty principle that uses signal sparsity or the number of non-zero coefficients. Let x n equals x 0 x 1 x n minus 1. Display style left math BF x underscore n right equals x underscore 0 x underscore 1 L dots x underscore n 1 be a sequence of n complex numbers and x k equals x 0 x 1 x n minus 1. Display style left math BF x underscore k right equals x underscore 0 x underscore 1 L dots x underscore n 1. Its discrete Fourier transform. Denote by x 0 display style x underscore 0 the number of non-zero elements in the time sequence x 0 x 1 x n minus 1. Display style x underscore 0 x underscore 1 L dots x underscore n 1 and by x 0 display style x underscore 0 the number of non-zero elements in the frequency sequence x 0 x 1 x n minus 1. Display style x underscore 0 x underscore 1 L dots x underscore n 1. Then n x 0 x 0 display style n leq x underscore 0 c dot x underscore 0. Benedicks' theorem. Amrine-Berthier and Benedicks' theorem intuitively says that the set of points where f is non-zero and the set of points where is non-zero cannot both be small. Specifically, it is impossible for a function f in L2 R and its Fourier transform to both be supported on sets of finite Lebesgue measure. A more quantitative version is f L 2 R D C E C S sigma f L 2 S C plus f caret L 2 sigma C display style f underscore L caret 2 math BF R caret D LEQCE caret C S sigma BIGL F underscore L caret 2 S caret C plus hat F underscore L caret 2 sigma caret C big R tilde. One expects that the factor CEC S sigma may be replaced by CEC S sigma 1 D, which is only known if either S or sigma is convex. Topic: Hardy's uncertainty principle. The mathematician G. H. Hardy formulated the following uncertainty principle: it is not possible for Fn to both be very rapidly decreasing. Specifically, if f in L 2 R display style L caret 2 math B R is such that f x c 1 plus x n e minus a pi x 2 display style f x leq 1 plus x caret n e caret a pi x caret 2 and f caret she c 1 plus she n e minus b pi she 2 display style hat f she leq 1 plus she caret n e caret b pi she caret 2 c greater than 0 n display style c greater than 0 n an integer, then if ab greater than 1 f topic 0 while if ab 1, then there is a polynomial p of degree n such that f x equals p x e minus a pi x 2 display style f x equals p x e caret a pi x caret 2. This was later improved as follows: if f element of L 2 R D display style f in L caret 2 math b R caret D is such that R D R D f x f caret she e pi x she 1 plus x plus she n dx d she plus infinity display style int underscore math b R caret D int underscore math b R caret D f x hat f she frac e caret pi Langle x she wrangle 1 plus x plus she caret n dx d she then f x equals p x e minus pi a x x display style f x equals p x e caret pi Langle x x wrangle tilde, where p is a polynomial of degree n minus d 2 and A is a real d times d positive definite matrix. This result was stated in Borling's complete works without proof and proved in Hormander. The case d equals 1, n equals 0, display style d equals 1, n equals 0, and Benami, Demange, and jamming for the general case. Note that Hormander-Borling's version implies the case AB greater than 1 in Hardy's theorem, while the version by Benami-Demange jamming covers the full strength of Hardy's theorem. A different proof of Borling's theorem based on Liouville's theorem appeared in Ref, a full description of the case AB. If a tempered distribution f element of S R D display style f in math call S math b R caret D is such that e pi x 2 f element of S R D display style e caret pi x caret 2 f in math call S math b R caret D and e pi she 2 f caret element of S R D display style e caret pi she caret 2 hat f in math call S math b R caret D tilde then f x equals p x e minus pi a x x display style f x equals p x e caret pi Langle x x wrangle tilde for some convenient polynomial p and real positive definite matrix A of type D times D. History. Werner Heisenberg formulated the uncertainty principle at Niels Bohr's Institute in Copenhagen, while working on the mathematical foundations of quantum mechanics. In 1925, following pioneering work with Hendrik Kramers, Heisenberg developed matrix mechanics, which replaced the ad hoc old quantum theory with modern quantum mechanics. The central premise was that the classical concept of motion does not fit at the quantum level, as electrons in an atom do not travel on sharply defined orbits. Rather, their motion is smeared out in a strange way. The Fourier transform of its time dependence only involves those frequencies that could be observed in the quantum jumps of their radiation. Heisenberg's paper did not admit any unobservable quantities like the exact position of the electron in an orbit at any time, he only allowed the theorist to talk about the Fourier components of the motion. Since the Fourier components were not defined at the classical frequencies, they could not be used to construct an exact trajectory, so that the formalism could not answer certain overly precise questions about where the electron was or how fast it was going. In March 1926, working in Bohr's institute, Heisenberg realized that the non-commutativity implies the uncertainty principle. This implication provided a clear physical interpretation for the non-commutativity, and it laid the foundation for what became known as the Copenhagen interpretation of quantum mechanics. Heisenberg showed that the commutation relation implies an uncertainty, or in Bohr's language a complementarity. Any two variables that do not commute cannot be measured simultaneously. The more precisely one is known, the less precisely the other can be known. Heisenberg wrote, it can be expressed in its simplest form as follows: one can never know with perfect accuracy both of those two important factors which determine the movement of one of the smallest particles—its position and its velocity. It is impossible to determine accurately both the position and the direction and speed of a particle at the same instant. In his celebrated 1927 paper, Über den anschaulichen Inhalt der quantentheoretischen Kinematik und Mechanik, on the perceptual content of quantum theoretical kinematics and mechanics, Heisenberg established this expression as the minimum amount of unavoidable momentum disturbance caused by any position measurement, but he did not give a precise definition for the uncertainties delta x and delta p. Instead, he gave some plausible estimates in each case separately. In his Chicago lecture he refined his principle. Kennard in 1927 first proved the modern inequality where h equals h, 2 pi, and sigma x, sigma p are the standard deviations of position and momentum. Heisenberg only proved relation 2 for the special case of Gaussian states. Terminology and translation. Throughout the main body of his original 1927 paper, written in German, Heisenberg used the word Ungenauigkeit, Indeterminacy, to describe the basic theoretical principle. Only in the endnote did he switch to the word Unsicherheit, uncertainty. When the English-language version of Heisenberg's textbook, The Physical Principles of the Quantum Theory, was published in 1930, however, the translation, "uncertainty", was used, and it became the more commonly used term in the English language thereafter. Heisenberg's microscope. The principle is quite counterintuitive, so the early students of quantum theory had to be reassured that naive measurements to violate it were bound always to be unworkable. One way in which Heisenberg originally illustrated the intrinsic impossibility of violating the uncertainty principle is by utilizing the observer effect of an imaginary microscope as a measuring device. He imagines an experimenter trying to measure the position and momentum of an electron by shooting a photon at it. Problem 1: if the photon has a short wavelength, and therefore, a large momentum, the position can be measured accurately. But the photon scatters in a random direction, transferring a large and uncertain amount of momentum to the electron. If the photon has a long wavelength and low momentum, the collision does not disturb the electron's momentum very much, but the scattering will reveal its position only vaguely. Problem 2: if a large aperture is used for the microscope, the electron's location can be well resolved, see Rayleigh criterion, but by the principle of conservation of momentum, the transverse momentum of the incoming photon affects the electron's beamline momentum and hence, the new momentum of the electron resolves poorly. If a small aperture is used, the accuracy of both resolutions is the other way around. The combination of these trade-offs implies that no matter what photon wavelength and aperture size are used, the product of the uncertainty in measured position and measured momentum is greater than or equal to a lower limit, which is up to a small numerical factor equal to Planck's constant. Heisenberg did not care to formulate the uncertainty principle as an exact limit, which is elaborated below, and preferred to use it instead, as a heuristic quantitative statement, correct up to small numerical factors, which makes the radically new noncommutativity of quantum mechanics inevitable. Critical reactions. The Copenhagen interpretation of quantum mechanics and Heisenberg's uncertainty principle were, in fact, seen as twin targets by detractors who believed in an underlying determinism and realism. According to the Copenhagen interpretation of quantum mechanics, there is no fundamental reality that the quantum state describes, just a prescription for calculating experimental results. There is no way to say what the state of a system fundamentally is, only what the result of observations might be. Albert Einstein believed that randomness is a reflection of our ignorance of some fundamental property of reality, while Niels Bohr believed that the probability distributions are fundamental and irreducible, and depend on which measurements we choose to perform. Einstein and Bohr debated the uncertainty principle for many years. The ideal of the detached observer. Wolfgang Pauli called Einstein's fundamental objection to the uncertainty principle, "the ideal of the detached observer", phrase translated from the German, "like the moon has a definite position." Einstein said to me last winter, "Whether or not we look at the Moon, the same must also hold for the atomic objects, as there is no sharp distinction possible between these and macroscopic objects. Observation cannot create an element of reality like a position, there must be something contained in the complete description of physical reality which corresponds to the possibility of observing a position, already before the observation has been actually made." I hope that I quoted Einstein correctly. It is always difficult to quote somebody out of memory with whom one does not agree. It is precisely this kind of postulate which I call the ideal of the detached observer. Letter from Pauli to Niels Bohr, February 15, 1955. Einstein's slit. The first of Einstein's thought experiments challenging the uncertainty principle went as follows. Consider a particle passing through a slit of width d. The slit introduces an uncertainty in momentum of approximately h, d because the particle passes through the wall. But let us determine the momentum of the particle by measuring the recoil of the wall. In doing so, we find the momentum of the particle to arbitrary accuracy by conservation of momentum. Bohr's response was that the wall is quantum mechanical as well, and that to measure the recoil to accuracy delta p, the momentum of the wall must be known to this accuracy before the particle passes through. This introduces an uncertainty in the position of the wall and therefore the position of the slit equal to h, delta p, and if the wall's momentum is known precisely enough to measure the recoil, the slit's position is uncertain enough to disallow a position measurement. A similar analysis with particles diffracting through multiple slits is given by Richard Feynman. Einstein's box. Bohr was present when Einstein proposed the thought experiment which has become known as Einstein's box. Einstein argued that Heisenberg's uncertainty equation implied that the uncertainty in time was related to the uncertainty in energy, the product of the two being related to Planck's constant. Consider, he said, an ideal box, lined with mirrors so that it can contain light indefinitely. The box could be weighed before a clockwork mechanism opened an ideal shutter at a chosen instant to allow one single photon to escape. We now know, explained Einstein, precisely the time at which the photon left the box. Now, weigh the box again. The change of mass tells the energy of the emitted light. In this manner, said Einstein, one could measure the energy emitted and the time it was released with any desired precision, in contradiction to the uncertainty principle. Bohr spent a sleepless night considering this argument, and eventually realized that it was flawed. He pointed out that if the box were to be weighed, say by a spring and a pointer on a scale, since the box must move vertically with a change in its weight, there will be uncertainty in its vertical velocity and therefore an uncertainty in its height above the table. Furthermore, the uncertainty about the elevation above the Earth's surface will result in an uncertainty in the rate of the clock. Because of Einstein's own theory of gravity's effect on time. Through this chain of uncertainties, Bohr showed that Einstein's light box experiment could not simultaneously measure exactly both the energy of the photon and the time of its escape. EPR paradox for entangled particles. Bohr was compelled to modify his understanding of the uncertainty principle after another thought experiment by Einstein. In 1935 Einstein, Podolsky and Rosen (CEPR paradox) published an analysis of widely separated entangled particles. Measuring one particle, Einstein realized, would alter the probability distribution of the other, yet here the other particle could not possibly be disturbed. This example led Bohr to revise his understanding of the principle, concluding that the uncertainty was not caused by a direct interaction, but Einstein came to much more far-reaching conclusions from the same thought experiment. He believed the natural basic assumption that a complete description of reality would have to predict the results of experiments from locally changing deterministic quantities, and therefore would have to include more information than the maximum possible allowed by the uncertainty principle. In 1964, John Bell showed that this assumption can be falsified, since it would imply a certain inequality between the probabilities of different experiments. Experimental results confirm the predictions of quantum mechanics, ruling out Einstein's basic assumption that led him to the suggestion of his hidden variables. These hidden variables may be hidden because of an illusion that occurs during observations of objects that are too large or too small. This illusion can be likened to rotating fan blades that seem to pop in and out of existence at different locations and sometimes seem to be in the same place at the same time when observed. This same illusion manifests itself in the observation of subatomic particles. Both the fan blades and the subatomic particles are moving so fast that the illusion is seen by the observer. Therefore, it is possible that there would be predictability of the subatomic particles' behavior and characteristics to a recording device capable of very high-speed tracking. Ironically, this fact is one of the best pieces of evidence supporting Karl Popper's philosophy of invalidation of a theory by falsification experiments. That is to say, here Einstein's basic assumption became falsified by experiments based on Bell's inequalities. For the objections of Karl Popper to the Heisenberg inequality itself, see below. While it is possible to assume that quantum mechanical predictions are due to non-local, hidden variables, and in fact David Bohm invented such a formulation, this resolution is not satisfactory to the vast majority of physicists. The question of whether a random outcome is predetermined by a non-local theory can be philosophical, and it can be potentially intractable. If the hidden variables are not constrained, they could just be a list of random digits that are used to produce the measurement outcomes. To make it sensible, the assumption of non-local hidden variables is sometimes augmented by a second assumption that the size of the observable universe puts a limit on the computations that these variables can do. A non-local theory of this sort predicts that a quantum computer would encounter fundamental obstacles when attempting to factor numbers of approximately 10,000 digits or more, a potentially achievable task in quantum mechanics. Popper's criticism. Karl Popper approached the problem of indeterminacy as a logician and metaphysical realist. He disagreed with the application of the uncertainty relations to individual particles rather than to ensembles of identically prepared particles, referring to them as statistical scatter relations. In this statistical interpretation, a particular measurement may be made to arbitrary precision without invalidating the quantum theory. This directly contrasts with the Copenhagen interpretation of quantum mechanics, which is non-deterministic but lacks local hidden variables. In 1934, Popper published Zur Kritik der Ungenauigkeitsrelationen, Critique of the Uncertainty Relations in Naturwissenschaften, and in the same year Logik der Forschung, translated and updated by the author as The Logic of Scientific Discovery in 1959, outlining his arguments for the statistical interpretation. In 1982, he further developed his theory in quantum theory and the schism in physics, writing, Heisenberg's formulae are, beyond all doubt, derivable statistical formulae of the quantum theory. But they have been habitually misinterpreted by those quantum theorists who said that these formulae can be interpreted as determining some upper limit to the precision of our measurements. Original emphasis. Popper proposed an experiment to falsify the uncertainty relations, although he later withdrew his initial version after discussions with Weizsäcker, Heisenberg, and Einstein. This experiment may have influenced the formulation of the EPR experiment. Topic: Many worlds uncertainty. The many worlds interpretation, originally outlined by Hugh Everett III in 1957, is partly meant to reconcile the differences between Einstein's and Bohr's views by replacing Bohr's wave function collapse with an ensemble of deterministic and independent universes whose distribution is governed by wave functions and the Schrödinger equation. Thus, uncertainty in the many worlds interpretation follows from each observer within any universe having no knowledge of what goes on in the other universes. Free will. Some scientists including Arthur Compton and Martin Heisenberg have suggested that the uncertainty principle, or at least the general probabilistic nature of quantum mechanics, could be evidence for the two-stage model of free will. One critique, however, is that apart from the basic role of quantum mechanics as a foundation for chemistry, non-trivial biological mechanisms requiring quantum mechanics are unlikely, due to the rapid decoherence time of quantum systems at room temperature. The standard view, however, is that this decoherence is overcome by both screening and decoherence-free subspaces found in biological cells. The second law of thermodynamics. There is reason to believe that violating the uncertainty principle also strongly implies the violation of the second law of thermodynamics. See also Notes